Good morning, everybody. I'm Mike Griffin, and privileged to introduce another of our ARMD tech seminars, pioneered by Lisa Porter and her staff to reacquaint some of us at NASA headquarters with what goes on in what's really important at NASA, and that's our technical work. These seminars, I'm told, are also doing quite well throughout NASA at our field centers, where people watch them in real time or on tape. So I'm pleased we're doing these things. Thanks, Lisa. Today's seminar is by Paul Dennehy, who received his bachelor's in mechanical engineering from University of New Hampshire in 1989, and then got master's and doctorate degrees in mechanical engineering from Stanford in 91 and 95, respectively. His PhD thesis work was experimental and was completed at the Combustion Research Facility at Sandia National Labs in California. Between 1995 and 2000, he worked in the physics department at the Australian National University in Canberra, first as a postdoc and then as a faculty member. Since 2000, he's been working at NASA Langley Research Center, where he is currently in the Advanced Sensing and Optical Measurement branch of the Research and Technology Directorate. He leads research teams studying hypersonic flow and supersonic combustion. He's an associate fellow in the AIAA and represents NASA on the AIAA Aerodynamic Measurement Technology Technical Committee. He's produced over 100 publications, including 30 of them in peer-reviewed journals, and in the past 6 years has won 2 Outstanding Paper Awards and a Best Paper Award from AIAA technical committees. None of those are things I ever won, so I'm impressed. And Paul, real pleased to be introducing you for your topic today. Thank you for being here. Thank you.
Thanks for having us.
The floor is yours.
All right. So I'm Paul Dennehy from NASA Langley, and I first want to thank the ARMD and the Hypersonics program for selecting me to present to you today. First chart, please. Next chart. I'm going to be talking about 3 different measurement techniques. For the moment, I'll just describe them as CARS, IRS, and PLIF. So I'm going to introduce those techniques, talk about some of the measurements that we've done, and discuss some of our future capabilities and plans before concluding. Next chart, please. I first want to recognize the contributions made by some of our team members. First, the CARS Rayleigh team. Sarah Tedder and Daniel Buvlaru have been instrumental in the current work we're doing. Sean O'Byrne was a postdoc who did a lot of work, and Andrew Cutler was my closest collaborator on this work. Furthermore, we interact closely with several members of the Hypersonics propulsion program, and the subject matter experts help us decide what to work on so that we keep our work relevant. We've also had some help with some experimental design folks, and of course the people operating the wind tunnels have been very critical. Next chart. For the nitric oxide PLIF work, I want to particularly recognize the contribution from Jennifer Inman, who completed her PhD recently and was recently hired by NASA. And also, again, we worked closely with the aerodynamics experts to come up with the topics that we're going to work with, both university and local and NASA-wide researchers. And most of our work has been done in the 31-inch Mach 10 wind tunnel at Langley, and I want to recognize the contribution of those folks. Next chart. So the topic of my talk is, the title is Exploring Hypersonic Flow Using Laser Spectroscopy. Most people know what hypersonic flow is, but let me spend a moment and explain what laser spectroscopy means. Laser spectroscopy involves using lasers and cameras to make measurements in wind tunnels. And in the wind tunnel environment, it's very difficult to see particles in the flow, so in particular what we're doing in this case is looking at the molecules that are there, such as nitrogen and other gases. Using these techniques, we can make measurements of the flow field, visualization of the flow field, and also quantitative measurements. Some advantages of using laser spectroscopy are that you can make very fast measurements, maybe on the order of a microsecond or shorter, that freeze the flow. They're also non-intrusive, so the measurements can be made without, for example, a probe where the shock wave might form on a probe in a hypersonic flow, and also remotely. Next chart. So some of you have seen this chart before, but I want to explain this chart in a slightly different way, which is, okay, there's two main focuses in the hypersonics program. One is this high mass Mars entry, HMME. And what I want to explain here is how the laser spectroscopic measurements can be used to make measurements in these flows and how they can contribute to these programs. So if we start in the top left corner, first thing we can determine, for example, the boundary layer thickness and the state of the boundary layer on the forebody of an entering vehicle. We can also look at the shock wave that might form on on an entry vehicle. And going clockwise, we can look as the gas flows around the corner of the shoulder of the entry vehicle, it can become turbulent and impinge on the vehicle. So we can look at, for example, where that impingement point is and determine whether the flow is laminar or turbulent in that shear layer. We can also measure the size of that separation region. Passing further around on the bottom right-hand corner, we can image reaction control system jets if they're present on the vehicle to steer the vehicle. At the bottom, we can also visualize shock-shock interactions that might occur, for example, if there was a control surface. And finally, we can observe ablation and transition on the forebody of an entry vehicle. And so these are all things that laser spectroscopic measurement techniques can do for the HMME class. Next chart. The other class of vehicles the hypersonics program is interested in studying is highly reliable, reusable launch systems. And one of the best technologies for that type of measurement, or that type of launch system, is a scramjet engine. And so let me very briefly explain what a scramjet engine is. It's a rectangular duct. It's a very simple concept, but difficult in practice to achieve. It's a rectangular duct with no or very few moving parts. Gas flows left to right in the reference frame of the vehicle here. The vehicle is already moving at some Mach 6 or Mach 10. And for example, the gas becomes compressed by the shock waves that are on the inlet of the vehicle. After it's compressed, fuel is injected, and then it burns. And the expansion of that burning fuel provides thrust. Next. So what can we do to help study this flow is we can, again, determine the inlet boundary layer thickness, the state, laminar versus turbulent of the boundary layer. We can measure the velocity profile. We can visualize shock waves and interactions on the in the inlet of the vehicle. We can quantify the fuel-air mixing and the penetration of the fuel jets. We can measure the radical species formation and consumption, which are critical to the ignition process. And at the exit of the engine, we can also measure the temperature rise, the velocity, the exit composition, and that can give us information about the efficiency of the combustion process and also possible pollution that could be formed. So these different quantities that we measure, our goal is to make accurate measurements and then compare them with computational fluid dynamics codes. And furthermore, if we have good quality measurements, we can actually develop new physics models, for example, for chemistry or turbulence or their interactions, because the typical models that are used in designing scramjet engines, for example, those are based on incompressible subsonic non-reacting data, and then there's various correction terms to try to make them applicable to these. But most of the data sets that they're based on are not the regime that they're being used in now. Next chart. So what I'm interested in, and our team is interested in, is using lasers to make measurements in interesting flow fields. We're interested in making quantitative measurements where possible, so temperature, pressure, velocity, mole fraction, for example. The things we care about are the accuracy of the measurements, the spatial precision, the temporal precision, and the reliability of the techniques. And our general scheme is to, first of all, understand the optical process and the physics of that process, and then if we can understand that process, we can then exploit it to make a measurement. Now, there are loads of good applications of good measurement techniques that already exist, and unfortunately, there's no one tool that solves all the problems. And so they're very niche applications, and I also want to point out that they can be really quite expensive and complicated efforts that require often a PhD-level researcher. Next chart. So before I start talking about our work, I want to mention a couple important points, which are that these techniques, like I'm about to describe, are available in all flow regimes, subsonic, supersonic, and hypersonic. And I've listed a number of cases here. Particle image velocimetry, PIV, is a wonderful technique, that's a very powerful technique, but it's not spectroscopic because it does actually use particles, but it's easily implemented in subsonic flows. There's also numerous other techniques that are being employed by NASA and Air Force, industry, and universities throughout these flow regimes. And I also wanted to point out that within the Hypersonics program, there's a lot of good work being done in the area of laser spectroscopy at the various aero centers, Ames, Glenn, and Langley. Next chart. So now to start talking about the technical details a little bit, I'm going to first talk about the technique Rayleigh scattering. And this Rayleigh scattering, if you imagine this experiment in the bottom right where you pass a laser beam through some gas flow and you image it somehow with a camera or some other detector. Rayleigh scattering is the strongest phenomena of scattering that you observe in a clean gas. If there's particles in the gas, then you would see Mie scattering, that's scattering from particles. So this technique of Rayleigh scattering, which the color of light that's scattered is basically the same as the laser's frequency, approximately, can be used to measure temperature, density, and velocity of the gas. And the way that works is shown in this bottom left schematic here, where it's a graph of the intensity of light versus the frequency. And if the narrow peak on the left, if we think of that as the laser's frequency, then the scattered light from the Rayleigh scattering is going to be spectrally broadened by thermal motion of the molecules. And if there's a velocity of the gas, it will be Doppler shifted. And also, so that you can measure the velocity from the Doppler shift, the temperature from the width of the spectrum, and the height of the spectrum can tell you the density of the gas if you know the composition of the gas. So that's a powerful technique, and I'll be explaining that in more detail later. Next chart. Raman scattering is a similar process to Rayleigh scattering, but whereas Rayleigh scattering is, maybe one photon out of a million gets scattered, Raman scattering is even weaker, maybe another 100 or 1,000 times weaker. But during a Raman scattering event, the energy of the molecule changes. So if we draw an energy level diagram, and first of all, if we think about our molecule, our nitrogen molecule there, it's a molecule that can rotate, it can vibrate, and it has an electron whizzing around the outside. Now, during the process of scattering, the energy of a molecule can stay the same, and that's Rayleigh scattering. And it's represented by an arrow incident and outgoing arrows of energy that are the same energy. If during the process the molecule gains a little bit of energy, it starts rotating a little faster, for example, then the scattered light, the photon, is redshifted. And if the molecule slows down, then some of that energy has gone into make that photon a little bit bigger, and you get a blue scattered photon. So Raman scattering is another very powerful technique which is able to make quantitative measurements, species concentrations, for example. Next chart. So Rayleigh and Raman scattering are linear processes, and scattering is in all different directions around the laser beam. The technique I want to talk about now, CARS, is a similar process involving some of the same physics, but scattering is into a laser-like coherent laser beam. And it's kind of like magic. You put in 3 laser beams and you get a 4th one out. So the big advantage of this laser-like beam is that in a facility, for example, like a scramjet engine where you have a ducted flow and you have windows, you can have much better optical access. You can have much better, higher signal intensities collected through small windows because of this laser-like beam that can propagate out. Unfortunately, it's a more complicated technique. So the way this works is, so it's coherent anti-Stokes Raman scattering, CARS, and it involves a sequence of these Raman-type processes. The first one is called a Stokes process, and the second one is an anti-Stokes Raman process. And basically all 3 of these, the first 3 laser beams with 2 reds, two greens and 1 red, are there coincidentally in time, and it generates this 4th beam, which is blue. Next chart. So how we do that in the laboratory is we take 3 laser beams, say 2 greens and 1 red, and they're all collimated, and they pass through a lens which focuses them to a small point. At that point in the flow, our species of interest is there, for example, nitrogen, and those beams interact with that nitrogen, and it produces a 4th laser beam, which is blue. And if we make the red beam a spectrally broad beam and the green beam monochromatic, then we get a spectrally broad blue beam coming out. Next chart. If we disperse that spectrum on a spectrometer, then we see spectra that look like these. These are actually calculated spectra. And if we look at the top right-hand graph, if we hold the concentration of nitrogen constant in this calculation and vary the temperature, you see that you start out at low temperature with just one spike in the spectrum. At higher temperature, additional vibrational bands are populated, and therefore we can actually determine the temperature from the measured spectrum. Below that, we see that if we hold the temperature constant and vary the concentration of nitrogen, the relative amplitude of this background and the peak change, and therefore we're sensitive to composition. So what we do is we take an experimental spectrum, and then we have a calculation that is, we have a library of a library of spectra that we use to do a best fit, determine our temperature and concentration. Next chart. And I also just want to show one quick result showing you that we try to do measurements in a calibrated environment. So we know we get the right answer when we compare with a thermocouple, for example, and so we trust that we're getting valid results. We make measurements in flames and furnaces. Next chart. So the first results I want to show you are in a scramjet combustor model, which is was selected by a NATO research and technology organization working group. They chose this configuration as a benchmark data to provide CFD validation in about 2000, which was the year I was hired. This involves hot air produced by the direct connect supersonic combustion test facility. It goes in the left side of this engine, and there's a step on the top wall, and then hydrogen fuel, room temperature hydrogen fuel, is injected at Mach 2.5, and it penetrates into the flow. And we have slots cut in the walls of the duct, and we can make measurements at those 7 planes there, 1, 3, 5, 6, and 7. And we have it's a point-wise technique. What we do is we have a stepper motor system that moves that point to different locations in the flow. So one challenge we have is that it's very time-consuming to make these measurements, and so it takes a whole day of operating the wind tunnel just to obtain one plane of measurements. Another challenge we have is that once we go into this facility, there are these submarine doors that have to be locked up after we get everything running, and then we can't go in again until the end of the day. So we have to be able to design for that, have our remote operation of our optics. A third big challenge is, for safety reasons, we have to flow outside air through the room. So if it's 90 degrees and 90% humidity outside, that's what you have inside. And if it's snowing outside, it's snowing on your lasers. So it's a real challenge. Next chart. We use a formal design of experiments approach using the normal methods of randomizing, replicating, and then fitting response surfaces to the measurement points. Each one of those grids that you see is a series of thousands of points showing where we've actually made the measurements. And using this design of experiments approach allows us to defend against systematic errors, and also we've calculated that we can get the same accuracies using this compared to the conventional approach, but we can do it by acquiring 5 times less data. So, next chart. So here we see a cutaway view of our duct where flow is coming from the top left to the bottom right, and it's the same combustor I showed you a moment ago. So at plane 1, these are temperature maps. Plane 1, we see a nice uniform temperature coming into the combustor. Between planes 1 and 3, the fuel's been injected, so that blue spot there is cold hydrogen fuel. That fuel penetrates, but it hasn't burnt very much, even by plane 5. And then between planes 5 and 6, it really starts to burn. And particularly it burns in the top and in the bottom of the jet and a little bit of an annular region around it. And that process just continues down to the last measurement station. Next chart. So after we did those measurements, that was successful, but we also wanted to be able to have species concentration measurements simultaneous with these type of temperature measurements. So we've changed our approach. Instead of using the conventional broadband cars method I explained previously, we switched over to dual pump cars, which was invented by Bob Lucht and coworkers. So with dual pump cars, all you do is swap out one of those green beams for a yellow beam, which is shown there on the top of the bottom chart. Next chart. So by using the combination of the red and green beams, we can still probe nitrogen, which was the species we were probing before, And it actually doesn't matter what color that third photon is in that Carr scattering process, it still generates the fourth photon. Now, by looking at the combination of the yellow and the red beams, we can now probe oxygen because their frequency difference corresponds to oxygen, the Raman resonance of the vibrational state of oxygen, that is. And then again, it doesn't matter what color that third photon is. The green works just fine. And finally, those two spectra that come out, the nitrogen and the oxygen, appear right next to each other on the spectrometer, which is very convenient compared to other methods of trying to do multiple species. So, and then when we tried this in the laboratory, we found out that there are also some hydrogen lines naturally present that are located there as well. So using this approach, we could look at nitrogen, oxygen, and hydrogen. And for hydrogen combustion, that's most of the, well, there's also water, but that's most of the species of interest. Next chart. So here are just two single-shot spectra taken in a combustor. If you look at the top right-hand corner, that's kind of a typical warm air spectrum showing nitrogen, the big peak, and the smaller peak is oxygen. The chart on the left shows, again, the nitrogen is hotter now. There's extra peaks showing there, the vibrational peaks. And then those really skinny peaks are hydrogen. So one spectrum, we can measure those, and then we can fit for those species concentrations. Next chart, and temperature. So this shows one slice across the duct where we've scanned our measurement point across the duct at one distance downstream. And if you look at the chart on the left, it's showing the raw data and the a fit to the data of temperature versus distance across the duct. And when you look at that, you say, gosh, that's noisy data. Well, that noise that we're seeing there is what we're interested in measuring. That's the turbulence in the flow. That's not caused by a measurement instrument. If you look in the top right-hand corner of the left-hand chart, that 4 sigma, that error bar that I've shown there is 4 sigma of our measurement uncertainty, basically. So what you're seeing, the scatter that you see in that chart is the turbulence that we're actually there to measure. If you look at the right-hand chart, you see the hydrogen concentration in green, the nitrogen concentration in blue, and the oxygen concentration going all the way to 0 in the center of the duct in red. Next chart. So this chart just shows a comparison between the measurements made and presented in 2002 with the measurements made and presented in 2004 using this same, using the 2 different methods, one the conventional Carr's technique and then the other one's a dual pump Carr's technique. And they're very similar temperature maps, which was comforting to us that we saw the same thing measuring 2 years apart. Next chart. But this new measurement also had the measurement of temperature in nitrogen and oxygen and hydrogen. So if we look, for example, at the nitrogen map, we again see the fairly uniform flow coming in. Then we see where the nitrogen's been displaced by hydrogen in plane 3. Plane 5 is propagated further down. And plane 7, we see that if you look at the scale on the left side of the charts, that some of the nitrogen actually made it all the way to the center of the flow. That's showing that nitrogen has penetrated, air has penetrated all the way to the flow, to the center of the fuel jet. If we look at the oxygen, on the other hand, again, we see the same jet penetration, but when we get to plane 7, that, if you look at the color bar there, that actually goes to 0. So the oxygen, all at the center of the flow, has been consumed. And this makes sense. Next chart. So this chart is showing a list of people who have requested our data sets for computational fluid dynamics validation. And it's a number of different research groups, including Sandia National Labs, various industrial within the United States, and many different universities. And the 2 I've highlighted with arrows there, they're actually using these data to create new turbulent transport models for combustion. Next chart, please. So the continuation of that experiment is going on right now, or the continuation of this technology. And what we decided to do after that highly three-dimensional flow that we just described, we wanted to simplify things and do an axisymmetric flow, but take a lot more data in those smaller location, smaller domain, thereby producing higher estimates of the uncertainties, or improved estimates of the uncertainties in the flow, in particular with the fluctuations. So in addition to measuring temperature and mole fraction, we also wanted to measure 2 components of the flow velocity. And so that opened up a new opportunity for us to develop more instrumentation. And this project of this unconfined axisymmetric reacting flow is also co-supported by the Department of Defense and NASA Hypersonics program. So we're looking now at a Mach 1.6 nozzle issuing into an ambient air in the Direct Connect supersonic combustion test facility at Langley. We have the option to flow through that co-flow a hydrogen jet, and we can actually produce stoichiometric fuel air mixing in that jet. And then on the right-hand side of that shows an infrared image of the resulting flow field. Next chart. So we're doing CARS spectroscopy just as we have previously, and that's represented here, the beams kind of coming up from the bottom and passing where the CARS signal is collected at the top left of this chart. But we're additionally adding this instrumentation, interferometric Rayleigh scattering. So that the Rayleigh scattering light is being collected by this lens that's shown there, and that green cone is showing the cone of light that's being collected. So with the Rayleigh scattering, we can measure two components of velocity. And next, so if the Rayleigh scattering is sensitive to the velocity component that's the bisecting angle between the two, the incident photon and the collected photon. So you see that we measure velocity component V1 from this incident angle, and when we retroreflect the green beam back through the flow, back to the same focus, next chart, we collect the other velocity component, okay, because that light is coming back and being collected by the signal. So we've collected two orthogonal velocity components with this approach. So using the combination of these two techniques, this is the most thorough characterization of supersonic combustion flow that's ever been performed. Next chart. Okay, so let me give you a few more details on how the Rayleigh scattering system works. If we imagine our laser beam is passing at the top left towards the right, where it says measurement volume, and then our Rayleigh scattering optics are collecting some of that light. What you see, if you forget about where it says etalon and reference, forget about that for a moment, and basically what the camera would see is an image of the laser beam at the focus. Next. So an image would look like this. You just see the focus of the laser beam. Okay. But if we use this etalon in place, an etalon is basically a piece of glass partially silvered on either side, and when you put that in place, there's interference that occurs, and it spectrally filters the light. So next. So what you see is a series of transmission peaks, and if those peaks move, well, the horizontal direction now is also a frequency indicator. So if those little peaks move side to side, that indicates a Doppler shift. Next chart. So the resulting image has both spatial and spectral information in this image. So, and furthermore, this reference beam has been put in everywhere, and so we get these circles having to do with the interference pattern of the etalon, and those provide a reference. And so when these little blobs that you see there, which are from the laser beam scattering, when they move relative to the reference, that determines the Doppler shift. Next chart. So we can look at that for low temperatures or high temperature flows. Here's a result for a high temperature flow where the velocity was moving about 1,000 meters per second. And we take spectra and process them, fit them with some Gaussians or some other sort of measurement system, and we can measure the Doppler shift. For example, on the right-hand graph there, V2 is showing a Doppler shift to the right relative to the reference. And so when we look at two different components of velocity, we spatially separate them on the detector so we can figure out which is which. Okay, and so the accuracy of this technique is around 10 to 40 meters per second in high temperature conditions, depending on the temperature, which is 1 to 4% of the velocities that you're interested in measuring. Next. So we've implemented this most recently in a mobile instrument because we didn't want to have to put our lasers in there in the snow and the humidity. So we built up and we also wanted to be able to develop it in the laboratory and then bring it to the facility later and then get it back to the laboratory in one piece. So we have this double-decker optical cart set up with a YAG laser on the bottom, pumping some dye lasers and a broadband dye laser up top. Next chart. Next chart. And here's a picture of the system. It's on wheels, and it all closes up for laser safety. And again, the YAG laser on the bottom, the gas or the light propagates to the top, and then off to the right-hand side where it says output mirror up to the facility, it sends the light up. And we're actually installed in the basement underneath the facility for just to make it easier, so we have access to the lasers during the operation of the test. Next chart. So in the facility, we have a very complicated system to collect the light, and a large cube that moves the measurement location around in the flow and carries the system, the Rayleigh scattering camera along with it. And that's shown schematically here, the laser beams coming in, focusing, and signal going off to the left, and the Rayleigh scattering optics to the right. This is set up in the direct connect supersonic combustion test facility. Next chart, please. This is a very busy picture showing how that's set up. The facility flow is actually coming from the left-hand side where it says flow direction, and it goes exhaust to the top center of the image. And on the right-hand side, you can see where it says IRS, EMCCD. That's the Rayleigh scattering collection optics, and all these beams are the stepper motor system that moves the measurement around. Next chart. So the current status of this experiment are that we have completed the development of the instrumentation. We are now doing the testing in the facility. We've completed the case of mixing where we had non-reacting fuel-air mixing, basically. And now where we're looking at the combustion cases, they're probably running today, looking at hydrogen co-flow. And we also would like to look at a hydrocarbon co-flow. And this data should be available in about 6 months after it's processed for our various customers. Next chart. So our future plans are closely involved with George Washington University, our collaborators there, who we have 2 NRAs with. That's been a really good mechanism to support them to collaborate with us. We want to extend the hydrocarbon, the ability of cars to make measurements in hydrocarbon flows by looking at, for example, ethylene or carbon dioxide. And also, with the Rayleigh scattering, we want to be able to develop the third component of velocity, and also to measure temperature and density in flows where we know the composition. So we are continuing to apply the techniques to combustion flows, and all this work that I just described is supported by these NRAs. There's, however, very much of an untapped potential to use interferometric Rayleigh scattering in both supersonic and hypersonic air flows, where in a number of different flow regimes, for example, you could measure temperature, density, 3 components of velocity at multiple points without any particle seeding or any other gas seeding. Next chart. So everything I've just talked to you about, cars and interferometric Rayleigh scattering, basically you're measuring at either a single point or a few points. Now I'm going to change gears, and we're going to talk about a 2-dimensional imaging technique called nitric oxide, planar laser-induced fluorescence, or NO-PLIF. Next chart. So this involves taking light out of a tunable laser, forming that light with some optics into a sheet, and if there's a gas flow that has some nitric oxide present in the flow, then the molecules are excited by the laser, and then the molecules fluoresce, and a CCD camera takes a picture of the fluorescence. Next chart. So if we think about back of our molecule, we have this molecule with this electron on the outside. What we're doing with laser-induced fluorescence is we're actually exciting that electron to another orbit, an outer orbit. And then after it's in that other outer orbit and it decides to come back down to the ground state, it gives off the photon. Okay, so it's that red-shifted photon that we're collecting. So the main thing that we're going to be looking at in this experiment is the intensity of the light that comes to the camera. And that intensity of light is much more complicated than this, but for our purposes today, the intensity of light you're going to see is proportional to the amount of NO that we've put into the flow. Okay, that's the first order approximation. Okay, next chart. So why are we using NO? Because it's a nasty, toxic, corrosive gas. We have to seed it in the flow. Well, we're using it because it has really good, favorable spectroscopy. It produces nice images. It's stable, so you can buy it in a bottle, and that way you can just seed it into a flow. It has a mass that's similar to air, so there's no questions of it slipping with respect to the other gas that might occur in a hypersonic flow. It has a very wide range of uses over large range of pressures, and in particular for the current application, it works very well at low pressures and hypersonic flows. And it's been used by a number of different universities and research institutions for quantitative measurements as well as flow visualization. So it shows a clear path of how to proceed in the future. Next chart. This is our mobile planar laser-induced fluorescence system. You can see that we have a little tow bar. You can drag it around. Again, it's YAG laser on the bottom, dye lasers on top, and then we convert the visible dye laser light to UV and then send it out the side and over to the facility. Next chart. So in this image here, we see our mobile PLIF system off to the left, our instrument rack in the front. Behind is the 15-inch Mach 6 wind tunnel. And we have a scaffolding up top that guides our laser beam over and down through the top window. Now, above the tunnel on the scaffolding is a stepper motor. And so with that stepper motor, we can scan the laser sheet span-wise across the flow to get three-dimensional information. Next chart. This chart shows a quick snapshot of some of the different research we've done with this nitric oxide PLIF technique. We were supported by the Return to Flight program between 2004 and 2006, which I'll show some of that work. But then since 2005, when the Hypersonics program was ramping up, we started a series of demonstration experiments mostly with existing models that we could find. And I'm going to be showing you a lot of those, maybe one chart at a time, of these different demonstration experiments we've done. Next chart. Some of those have led to more detailed investigations. For example, we've just completed this crew exploration vehicle RCS jet testing, which is going to have a follow-on test. And also some of the work led to more hypersonics-funded work, which was in this detailed flow over trips. So those three things I've highlighted there, I'm going to be explaining, detailing a lot more in the following charts. Next chart. So I'm going to do this by kind of application area, even though most of this work was, with the exception of this particular topic, has been supported by hypersonics. Okay, so this is the wing leading edge breach investigation that got us started on working with the folks in the hypersonics area. Next chart. So for this problem, what was needed was an ability to measure the flow patterns that would be internal to the wing of the space shuttle if there was a puncture in the wing. The question is, if there's a small hole, if it's a microscopic hole, then maybe you don't need to repair it because it's not going to cause any damage. If it's a huge hole, well, some other decisions are going to have to be made. But in the case of an intermediate-sized hole, they want to be able to predict what damage might occur on the inside of the wing of the space shuttle. If there was some strut that the jet might be impinging on, or something that would cause the vehicle to fail, then they'd have to do a repair. So they wanted to come up with a more quantitative understanding of this problem. And in particular, the thing they were really interested in is knowing whether the flow was going to be laminar or turbulent given a certain damage scenario. And the prior range of uncertainty before starting this experiment was about a factor of 10 in the Reynolds number, that they didn't know if the flow was going to transition. And they thought it was probably mainly just Reynolds number effects. So we did a series of experiments. I'll just show you one example of a free sonic jets today. Next chart. So, and start preparing for these experiments, we looked at using the Schlieren technique, which is the conventional measurement technique in hypersonic wind tunnel facilities for measuring gas flows for flow visualization. And so the apparatus that we used here was just a tube of nitrogen going through a sonic orifice and then expanding into a chamber that was held at a constant pressure. So there's no wind tunnel operating here. It was just a vacuum chamber, basically. So the Schlieren image showing on the left, you can barely make out some sort of barrel shock there, but it's not, you can't really see a lot of detail. The NO-PLIF image, on the other hand, which was taken the same day, shows very clearly the classic underexpanded shock structure. You have the barrel shock on the outside, top and bottom, and then that vertical line is called a Mach disk. The gas, it's a normal shock wave, and the gas downstream of that clearly shows turbulent flow. So this is an example of showing where nitric oxide PLIF is much more sensitive than the Schlieren technique at low pressures. Next chart. So the key things they were looking at was determining whether the flow is laminar or turbulent. And I'm showing you an example of a laminar image on the top. And this, again, is this underexpanded barrel shock, but with low enough Reynolds number, low enough pressures that the flow stayed laminar. And if I showed you 100 of those, you wouldn't be able to tell the difference. They all look just like that, very smooth. Maybe some high-frequency noise might change, but they're very, very smooth and regular. Turbulent flow, on the other hand, every image is different. You know, it's very random, jiggly, lots of different flow scales present. And, of course, the reason they're interested in turbulent flows is because there's a much higher heating level associated with turbulent flow, and they're much harder to predict. Next chart. So we came up with a fairly systematic, in fact, I'm going to point out Jennifer Inman, this is the topic of her dissertation work. She came up with a systematic method of analyzing these images where we take 100 images, calculate the mean and the standard deviation of those images, and then she quantified distances downstream where certain behavior would start occurring. For example, the distance where unsteady behavior started occurring, and then fully transitional behavior, then fully turbulent behavior. Next chart. And we could look at, here's an example of a series of experiments where we held the jet pressure ratio, which is the pressure ratio between the nozzle exit and the ambient. We held that constant at 14, and we varied the Reynolds number in the flow. And we did that by just increasing both those pressures, maintaining a constant ratio. And as you do that, if you look at the images on the left, you see the first image is laminar, second image starts to wobble a little bit, third image clearly becomes transitional, and the fourth image is highly turbulent. And if we look at that over on the standard deviation images, you can see those brightness in the standard deviation images propagating forward. Next chart. So by doing this with hundreds and hundreds of different runs, and then coming up with some clever scaling parameters, Jennifer was able to come up with a correlation that not only told them which flows became turbulent, which Reynolds number. It wasn't as simple as just a particular Reynolds number, because it turned out that the flow became turbulent depending both on the Reynolds number and on that jet pressure ratio. So it was more complicated than had been anticipated. And she was able to come up with this correlation that showed them how far downstream of the nozzle exit the flow became turbulent. And Boeing uses this data to determine which flow model to invoke when they are calculating a damage scenario. Next chart. So in addition to just that useful data that Boeing can use, we also were able to look at the physics of the transition process by, for example, if you look in the bottom right-hand corner, some of the jets started to wobble the top and the bottom of the jet together, and that's kind of a sinuous mode. It looks like a little sine wave. If you look to the left, the top and the bottom of the jet are kind of opposite sign, and you kind of pinch off little blobs. I think some people call it the sausage mode. And then if you look at the top, there's this azimuthal mode that when we looked at the top images, it wasn't immediately apparent what we were looking at there. But by scanning our laser sheet sideways through this laminar flow and then reconstructing later, we could see these star patterns in the cross sections. And those star patterns do lead to turbulence, transition to turbulence as well. So this is a nice data set that hopefully we can glean some more transition information out of. Next chart. So the impact of this work has been that, of course, that these correlations that we've developed allow Boeing to determine for a given impingement distance and angle whether the flow should be laminar or turbulent in their calculation, and also it identified some of the transition mechanisms that are causing these sonic and supersonic jets to transition. Next chart. Okay, so now I want to move on to work that's been supported by Hypersonic, but was motivated by the Space Shuttle Return to Flight program. I mean, I personally look at the Space Shuttle as a neat hypersonics problem with all kinds of interesting issues that make for good hypersonics experiments, such as cavity flows, gap filler, perturbations, and looking at the leeward wake flows. So next chart. These measurements were performed in the 31-inch Mach 10 wind tunnel at Langley. It's a blowdown tunnel. It can run for about a minute. We take images, 10 images per second, so we can document a lot of different activity during one run. It's a very nice facility to work in. There's no snow in this facility. Some rain, but no snow. We have big windows on the top, side, and bottom, and the model's injected from the fourth side of the tunnel. And we can get our cameras nice and close to this and get good magnification. Next chart. When we first get our images off our camera, they look like this. And if you're like most people, you'll say, well, gosh, I have no idea what I'm looking at here. So we use this technique called virtual diagnostic interface, which has been developed at Langley. And we convert these images, first of all, we might average some images, put a false color table on to enhance the contrast a little bit, and then render them on a computer model. Next chart. And then you can see more clearly what your experiment was. In this case, a challenge was from one of the researchers, can you visualize the aft body, the leeward side flow on a lifting body? And we happen to have this X33 model, so we put that in the tunnel, and we could see this flow. What we did was we seeded NO from near the stagnation point of the model up at the nose, and it flows downstream. And I don't know if you can see, there's a little kind of an upside-down mushroom wake vortex there. Next chart. Okay, so now I'm going to start talking about some other experiments. This one is simulating a missing or a damaged shuttle tile. And we developed this model. Well, this is an existing model again, where it's just basically a flat plate. It's mounted on a wedge. And we have some little instrumentation inserts that we could put in. So what we're doing is flowing nitric oxide out of some pressure ports near the leading edge of the model. And then the Mach 10 gas flows over that. And we image that region that's shown in that dark box there. Next chart. So if we have the angle at one particular angle, say minus 10 degrees, we first of all see the boundary layer coming in on the left-hand side of that image, and it's of a certain thickness, and it drops down into the cavity. And because our laser sheet is passing into the cavity, and our camera is actually above the cavity looking down, we can look into the cavity and see what's happening in there. So the flow, as you see, as it reaches the right-hand side of the image, it's impacting on the back wall of the cavity, and then keeps going. If we change the angle of the plate just 5 degrees, we first of all see the boundary layer got thicker, and then notice at the exit of the cavity, the gas seems to have missed that far corner. It seems to be skipping over the cavity. And also, it was notable that for this one experiment, this was a one-day quick experiment, but we didn't visualize any shock waves, which indicates to me that it could be that it's all subsonic flow in there. Next chart. Another experiment motivated by shuttle was to look at the turbulent heating to look at the flow patterns generated by these gap fillers, and there were rectangular and triangular gap fillers oriented 45 degrees to flow, which were poking out, and they could cause severe heating to the vehicle, which could have caused some problems. So on this particular mission, they were actually pulled out because they were very close to the nose of the vehicle. Next chart. Further to motivate this topic, there's the high-volt experiment in the Hypersonics program, hypersonic boundary layer transition, which is a fundamental experiment where they're looking both at smooth wall on one side and flow over discrete trips on the other side, and a flight experiment that's going to occur this year. Next chart. So to model this in the wind tunnel, we took that same flat plate I spoke of a minute ago, and we replaced that instrument module and drilled a little hole in it, plunked a little triangular piece of metal in there, and again, we're flowing NO out of the center line of the model. Next chart, please click on the figure. Actually, go back one. Click on the graphic, the movie. Thank you. And this shows our view of imaging. Okay. So shows the area that we're imaging, and the flow again is left to right over this trip. Okay, next chart. So if there's no trip present, then we see a nice laminar flow across the flat plate. With the trip present, the flow is laminar, and then just downstream it starts to wobble a little bit, and then it becomes highly transitional, but pretty organized in nature. Next chart. So the image I just showed you was with the laser sheet perpendicular to the flat plate. These images I'm going to show you now is where the flow is parallel, the laser sheet is parallel to the flat plate. So we're now getting a plan view or a top view of this. So, and also we've changed now, instead of flowing out of these holes, we're flowing out of a slot. So it's like a 2.5-inch wide slot there in this image. And so this is, again, a case with no trip, flows from left to right. And at first what we see is a kind of uniform flow, and then it starts developing into these tubes, or these tubular structures. And then if you look at the far right-hand side of this image, we see some corkscrew structures. Next. And we can zoom in on those corkscrew structures. So this is just some natural transition on a flat plate. Next chart. Okay, so we then put that triangular gap filler in. Again, this is a top view instead of the side view that we were seeing before. And we see the flow along the bottom of, so again, flows left to right. The flow along the bottom of the trip is staying laminar all the way across that image. The flow on the top side of the trip gets pushed way up, out along the boundary layer, and then it develops into these vortices, which first of all, one vortex will start turning into a corkscrew, and then it will often get the other vortex moving in sync with it. And next chart. And in this example, one of the vortices actually sort of wraps its arm around the other one. And so we're seeing some interesting flow patterns here. And note that that mechanism of transition seems to be different than the transition that's occurring directly downstream of the trip, where the kind of the right-hand bottom side of that right image, where it seems to have a different flow structure. So we're starting to be able to get at the real physical, understand what's happening in these flows, whereas before you would have to infer this from surface properties usually, like oil flow. Do you have any questions at this point, very briefly? Because this sometimes... Okay. Next chart. Okay, this was another interesting example where we look at, say, a pizza box trip, which basically looks like a pizza box thrown on a table. And the pizza box is representing a protruding shuttle tile. Okay, and so again, flows left to right in this image, and the flow as it comes to the pizza box trip gets diverted way around the outside, and we see all these different there's a lot of information in this image, horizontal streaks in the top and 45-degree angle streaks, and they all have to do with different flow patterns that we're observing. But this measurement is 1.5, the laser sheet is parallel to the surface and 1.5 millimeters off the surface. Next. This next chart is where we've scanned the laser much, much closer to the surface. And so one of the things you see is scatter off the surface. Some of these horizontal lines that you see in this image are where the different joints in the model go together, and you're seeing some scattered light. But the dominant thing I want to show you here is that the flow is laminar right at the surface. So 1.5 millimeters off the surface, turbulent, right at the surface, it's laminar. Next chart. So the next series of experiments were supported by the Hypersonics program and focused primarily on the Hypersonics program. Looking at planetary anti-wakes, capsule shear layers, and some ablation and boundary layer flow control. Next. So one of the researchers in the aerothermodynamics branch at NASA Langley challenged me with this particular capsule. This was a AGARD working group from the late 90s, and it's basically a Viking type forebody with this large separation on the back, on the aft body. And his frustration was that in order to measure the flow with hot wire to determine if it was laminar or turbulent flow in the past, he had to do a separate run at each position in the flow. So it took him many, many runs of the tunnel to probe out this wake flow, determine if it was laminar or turbulent. And with these densities, Schlieren wasn't able to do a good job of visualizing these flows. So I wanted to show him that in one image we could determine that this flow was either laminar or turbulent. And so what we did was we attached a tube to the sting, the support, and we supplied a little bit of nitric oxide in the wake flow, and it redistributes very quickly. It's very vigorous back there, and then it very clearly marks the difference between the recirculating flow in the separated region and the gas that's flowing over the top. So we see if you look at the top left image, the flow is kind of, that line is kind of straight, and then it starts to wobble, and then it becomes turbulent downstream. Next chart. Here's another example of wake flow imaging where we used an Apollo type model. We were again seeding NO along from a tube, and that we took a series of images like the one shown on the left, and we scanned our laser beam across the span-wise across the flow, and then reconstructed the images later in software, and it showed up these nice this sort of mushroom pattern that would be expected for flow over a capsule with a point source of seeding. Next chart. Then we tried, instead of seeding just the wake flow, we said, well, it would be nice to be able to visualize the shear layer in the flow that just marks the separated flow region and the gas passing over the top. So we took the pressure port that was closest to the shoulder of the cone at the top of the model there on the forebody and seeded a very low velocity of NO out of that, and it very clearly delineates the laminar shear layer on the top of the model. If we increase the flow rate by a factor of 5, you see the figure on the right, where we're actually get this kind of crazy transition where it's transitional on top but laminar on the bottom. So this is useful for just marking where the shear layer is. Next. But that also gave us the idea that maybe we could demonstrate, simulate localized ablation, where if there was a certain spot on the model that was getting an excessive amount of heat transfer, it might act as an ablation source, localized. And so we did this following experiment. We just did this a couple weeks ago. The NO is being flowed out of the center port of the heat shield. And at low flow rate, we have a nice laminar flow. At high flow rate, we can force the flow to become turbulent. And we could actually measure the critical flow rate that would cause the flow to become turbulent. Next chart. Similarly, we wanted to show that we could do measurements that were applicable to supersonic combustion, and we chose a configuration that had been well studied by Berry, Novak, and Horvath, where they had already done phosphor thermography and Schlieren and oil flow visualization on this same exact configuration, but they wished they had flow visuals, off-body flow measurements. So we repeated their conditions, and we showed that at the inlet of this inlet of a scramjet engine, when you blow at a low flow rate, the flow is laminar, and when we blow at a high flow rate, we can force the flow to become turbulent and provide them some off-body data. Now, of course, you might like a very turbulent flow going into your scramjet engine. That will increase the fuel-air mixing and also makes the flow more stable. Next chart. So now I want to switch to some work that's been motivated by Constellation program and supported by Hypersonics, and actually has also been supported by Crew Exploration Vehicle Aerothermodynamics program. Next. So we'll start, first of all, with this reaction control system jet visualization. We had this model that was set up in an Apollo-type configuration, and we looked at a pitch RCS jet. So we seeded NO at a 5% level into a nitrogen jet, and I think this was a Mach 3.5 jet, and that gas, as it went out, expanded, and we could visualize that trajectory of that jet with NO-PLIF. Next chart. So, for example, looking at the trajectory, we can quantify that by taking a series of our images and finding the maximum of the signal intensity versus distance downstream, and then we can graph that horizontal distance on the right and vertical distance on the left axis, and that would allow us to provide some CFD validation data for a case of, but we'd look at the standard deviation and the mean values of that. Next chart. So when we visualize these flows, it's also possible to combine them with a Schlieren image that shows the forebody shock, and that's a useful thing to do. But we still had the question with that RCS jet, why did it come up and then hang a right? Next. Well, it's because there's a shear layer there. And next. So if we superimpose those last two images, we see that that clearly is the reason that the jet is turning to the right. It's because it's impacting on that shear layer. So the combination of PLIF and the virtual diagnostics really can help us understand these flow features. Next. Okay, so next I'm going to be talking about this most recent work we've done with a reaction control system visualization, and it's going to play again. So this is the work that's supported by CEV. There's this barrel shock. You see it's got much bigger in this image, and it's also much more turbulent than in the last images we're showing because these are much more higher, more realistic flow rates. And also during that video you saw we swept our laser sheet back and forth to get that three-dimensional information, and we can reconstruct that later. Next. So when we did this experiment, we compared two different nozzle shapes. The one was a Mach 4.2 nozzle that was a conical nozzle, shown on the left, and on the right is a Mach 4.9 nozzle, which starts out with a contoured nozzle, then turns into a conical nozzle. And if you look carefully at these two images, you see in the far field, the jet looks about the same, but in the near field, they look different. Next. So in particular, if you look at this one on the right, you see these probably what are centerline focusing effects in the jet, and this was not anticipated they would be there, but that's probably because of the way the nozzle was designed. So when we repeat these experiments, we probably want to do a more careful job of designing that nozzle. Next chart. Okay, and we can also look at the shear layer visualization in this latest round of testing for CEV, where as we increase the flow rate of nitrogen out of the jet, and we visualize the shear layer, we can see that push that shear layer further and further out, thereby showing us the aerodynamic implications of using these RCS jets. Next chart. So another topic of interest is the crew exploration vehicle compression pads. There are going to be these special materials used at certain locations on the crew module where it adjoins the surface module, so that the place where they're going to connect. And because of the type of material is different, there'll be differential ablation. It's possible that they will either ablate, well, that they'll start out as like a recessed region, and then if they ablate slower than the material around them, then they'll end up poking out and being a protrusion. So we modeled this in our facility by taking our same flat plate that we looked at before and inserting 4 millimeter, 2 millimeter, 1 millimeter cylinders and also 1 millimeter cavity and looking at the flows downstream of those. And I'm just going to show you results from the 4 millimeter trip and the 1 millimeter trip. Next chart. Again, these can cause transition, and that's the concern, and increased heating. So with the 4 millimeter trip on the left, we see that the flow coming in is dramatically diverted around, and there's some interesting structures here. Just straight downstream of the wake, there's quite a bit of activity where you can see some shear layers and other flow patterns that will be interesting to compare with computations. And in the 1 millimeter trip on the right shows a much less of an influence. The boundary layer thickness in this case was around 1 millimeter. So clearly it's forcing the flow to transition as well. If we can then look at the side view of the 1 millimeter trip flow case, it's shown there on the right, and it shows how high those structures are penetrating out beyond the laminar boundary layer thickness that was there. And also it's showing where the flow right near the plate is staying laminar further along than the flow further out. Next chart. Okay, so now I want to switch to talk about some of our future work. We're going to be improving our system, and we've received some support from the NASC to do that, and also from the Hypersonics program. And I'll also talk about some of the quantitative data we hope to get with the PLIF technique. Next chart. So with our current laser system, we're getting a new laser system that's going to have about 10 times higher output power. It's going to open up some new opportunities for us. It should be more reliable because it's actually supported. The one we've been using right now is from the 80s, and I found it in the basement someplace. So it's good to be able to have that support to upgrade everything. We're also, NASC has given us a grant a project to improve, to make a duplicate system for PLIF, and that will allow us to make measurements in the lab with one system while the other system's installed in the facility. Also, with two systems, we should be able to take the technology to additional facilities. For example, the 20-inch Mach 6. The arc-heated scramjet test facility at Langley is particularly of interest to me because it already has nitric oxide in the free stream. We would not have to seed nitric oxide into that flow. And furthermore, we could take the systems off-site to make measurements with some of our other partners. We are also getting a new camera for the velocimetry, the work I'm going to explain in a moment. Next chart. So the velocimetry, there's two different capabilities we're going to be developing, velocity measurements and temperature measurements. For velocity measurements, the way this works is that a thin pencil-like laser beam excites some molecules, and then you just wait to take the picture for 500 nanoseconds, and during that time, the gas is moving, and so it moves over a few millimeters, and you have a high magnification camera, and you can take the picture, and you just calculate the velocity from the distance moved over the time delay. And we have previously demonstrated this at the Australian National University when I was there, and we've also been working on that at NASA Langley, and with this new camera, we should be able to do this on every pulse of the laser. Next chart. Also, PLIF can be used to make temperature measurements, and this is again work done at the Australian National University when I was there. It's flow over a cone, and you see the top right-hand corner. There's showing the region that's been imaged, and by selectively exciting different spectral lines of nitric oxide, one can probe low-lying quantum levels and high-lying quantum levels, and then doing some manipulation of those images to provide a temperature map, as is shown here. And the accuracy on that should be around 5%. Next chart. Another activity I want to point out is that we have an NRA at Ohio State that they're developing a very fast measurement system. Our images I've shown you are all taken at 10 hertz, so each image is uncorrelated with the previous image. It's, a football field's worth of gas goes by between those images. Whereas this system, it can put a pulse out every 5 microseconds, for example, and take images at that same rate, maybe to take 20 images. So we'll be able to get time-resolved movies of not only just flow visualization, but they're proposing to do velocity and temperature measurements as well. Next chart. So looking back at this, this kind of big picture chart, I want to just revisit this and point out that there's a lot of different offshoots, a lot of possible follow-on experiments that we can use this technology on. A couple of them planned, but the others are just possibilities at this point. But I think there's a lot of contributions that we can make. Next chart. So a couple more parting shots. I think that there's a little bit of a paradigm change here, is what I've noticed by working with people in the tunnels. One of the issues is that experimentalists that usually make measurements in wind tunnels, they really live on the model. And what I mean by that is almost all the data that they get is force and moment, pressure measurements on the surface of the model. Maybe they get heat transfer measurements or possibly a Schlieren image occasionally. But I would argue that it's the gas that's really the important part. That's what we model with CFD, computational fluid dynamics. And we really need to be able to see that gas flow and understand the gas flow in order to make to get the most out of our wind tunnel testing. And a lot of the experimentalists, when I show them the results we get, they have difficulty interpreting it or don't know what you could do with that information. And also we meet people who say things like, gosh, there's already plenty of transition data out there. I don't see why you need to do any more of this kind of research. Or, I just don't see how this is going to help me design a better scramjet engine. So we struggle with those types of characters, but most people really are quite receptive to the work. And I also wanted to say that these technologies are available in every flow regime, as I mentioned earlier. There are people working in this area, at DoD, universities, industry. There's quite a bit of off-the-shelf technology, but it can be expensive and time-consuming. Next chart. So one of the reasons, you might also ask, why are these diagnostics advancements being made now? CARS itself has been around since the 1970s, and NO-PLIF has been around since the 80s. And one of the big reasons is that it's a real challenge to implement these facilities these techniques in large facilities. And another problem has been that there really wasn't any specific funding for instrumentation, at least in the first 5 years. We had some support, but since the Hypersonics project has come along, we've had very specific instrumentation funding, and that's been great for us. It's allowed us to plan and integrate with other research areas. We've had very modest but solid procurement funds, and we've been given tunnel time to demonstrate our wares. And this basic research program has really helped us flourish. And so I want to thank the Hypersonics and the ARMD for that support. Next chart. So in conclusion, we have acquired benchmark data for supersonic combustion using the CARS and the interferometric Rayleigh scattering techniques, where we measure temperature, concentrations, and velocity. We've applied NO-PLIF imaging for numerous investigations. Most of these have been demonstration experiments. We hope to be more closely involved. We have researchers in the Hypersonics program, for example, who sent me some calculations a few days ago showing where they're using direct numerical simulation, Navier-Stokes, to calculate flow over these trips. So we're getting closer integrated there. We're also developing new measurement capabilities. We plan to use these on various NASA programs. So thank you very much. And if you can go to the very last chart, just the the thank you chart to motivate some discussion. So.
Thank you, Paul. I'm J.D. Harrington. I'm going to handle today's question and answer portion of today's presentation. I ask that if you have a question, if you would wait until we get a microphone to you and then identify yourself before you begin. With that, do we have any questions here in the headquarters auditorium? And I have a couple here in standby just in case. Okay, well, the first one I have here for you, Dr. Danahy, is laser diagnostics capabilities extendable to flight testing purposes?
Yes, there's been a pretty strong effort at the Air Force in the last year to use a technique which I had the acronym up there on the screen. It was tunable diode laser absorption spectroscopy. That's a technology that uses very small telecom equipment that can do measurements, for example, of temperature and velocity of the gas in a flight experiment. And I think they're planning to fly something in Australia upcoming, and NASA's working with those folks. And we have some NRA, so we're looking at that technology as well for our program.
Any questions here in headquarters? Well, I believe we have a question at Glenn.
Now, perhaps you can expand upon your jet geometry of the hull. For instance, if you have Propel showed that you have can generate a horseshoe vortex out of the holes, or in the case of Danny Wang's holes, you can actually generate a very laminar type flow. So perhaps you can explain a little bit more about your jet and the hole geometry that you used. And the other thing is that work at Ohio State is very exciting to me, anyhow, because when we did the combustion work at Wright-Patterson, we saw at high-speed movies, we saw lots of things which looked like turbulence. And in the steady state, in the cases which we did not see that, it would look like steady state flow. So even though it looks steady in the very small time frame period, it is very, very random.
So I'd like to address the second comment. One thing that we can do with our current instrument is we have time-resolved measurements, so we're making the measurements in about 500 nanoseconds. So we can see the flow fluctuate, so we can tell the difference between a truly steady flow and one that's fluctuating with our current instrument. But the advantage of the Ohio State approach is that they'll be able to do full time resolution, for example, in turbulent flows, and watch those eddies move across the screen and look at those eddies evolve. But yeah, I'm also very excited about that technology. The first question, I wasn't sure exactly what you're asking, but when we looked at the flow over the flat plate with blowing, which was the HyperX model, we were able to increase the flow. Every run, we used a different flow rate, so we could see the slow development of starting to see those vortices. Just the tubes of gas that came out. Basically, it was a row of 17 holes, and the flow would just have very nice straight lines at low flow rates. At higher flow rates, they'd have straight lines, and then they'd start to wobble a little bit. And as they go higher and higher, those wobbles move back up further upstream, and finally downstream you start to see a lot of transitional or turbulent structures, until that last image I showed you the two limits in that one image, and the last one is very, very turbulent flow. So that work will be reported at the Seattle AAA conference next summer.
One more go around here. Headquarters.
Hi, Paul. In your challenges slide, or your concluding slide at the end, you talked about, and actually you addressed this earlier in your talk, about some of the issues with employing these diagnostics in large facilities. Could you say a little bit more, perhaps, beyond the optical access concerns that you expressed, some of the issues associated with characterizing the free stream flow? And in order to do quantitative measurements, you really have to know what is entering the test article that you're doing the measurements off-body about.
I'm not sure I understand your question. I mean, we can measure the free stream flow with, for example, Rayleigh scattering and an airflow or some other measurement technique. There's a laser-induced thermal acoustics technique being developed at Langley, and they use that, for example, in the unitary plan wind tunnel to measure the velocity and the free stream of the flow. So we can characterize the free stream conditions. We could use CARS to characterize the temperature and concentration in the free stream. But we don't need to know necessarily what the conditions are in the free stream in order to make a measurement in another part of the flow. Is that what you're asking?
No, not so much your ability to make the measurement, but your ability to do proper analysis on that, because the free stream chemistry may be very different than what might otherwise be assumed unless a proper characterization is done up front.
Yeah, it's pretty important to understand what you've got coming in to the, and it's one of the reasons we made an effort to, for example, with our combustor measurements, we did a measurement upstream of where the fuel was injected, which, yeah, we try, and if you look very carefully at that data, you'd see that there was a bit of non-uniformity in the composition left to right in that facility, and we're not sure why that is, but when I showed that to Randy Voland, who was one of the lead researchers on the HyperX program, that was the one thing he thought was most interesting about the whole data set, was the variation in the incoming flow conditions. But we have not yet taken this technology to a really difficult environment like the 8-foot high temperature tunnel at Langley. That's going to be a real challenge if we, and I would like to do that, but that's another order of magnitude harder than what we've been doing so far. Just the shaking alone will be a real challenge.
I believe we have one more question out at Glenn.
Yeah, I'd just like to follow up on that one. I'm interested in your injection hole itself, the geometry of the hole. How many L over D? Is it sharp edge? Does it have a lip on it, or what's characteristic of the hole?
The holes were very small. I'm trying to remember. I don't offhand remember the diameter of the holes, but they were produced using an EDM, and I think there's a plenum underneath, and then there's this hole of through a material of some thickness, which I could provide to you if you want to send me an email. In fact, as I said, we're gonna write up those results. Those were very preliminary results. We just got those a few months ago, and I just showed you a couple pictures from them. But I can't really give you a lot of details right now. But I'd be very happy to do that at another time.
All right, I have one more question here that was given to me this morning that I found intriguing, Paul. Experimental and computational methods have their uncertainties. How do you address these in the validation process of this research?
Yeah, that's a good question. We really do ask the computational people to look at their uncertainties as well. I mean, we have various uncertainties that we might have in our experiment. It might be systematic errors or random errors. Of course, if you have random errors, you can just take more data and drive those down to a smaller level. But the systematic errors are really the big challenge. You want to try to address those by improving your instrument. But one of the things we can do, for example, by measuring, and going back to the case of the supersonic combustor, if we measure the fluctuations in the temperature or the velocity coming into our combustor, that really helps the computational people narrow down their uncertainties. So that can be very helpful. But you're right, when we go to make comparisons, we really have to scrub everything and make sure that both people, both experimentalists and the computational people, are really being very careful about reporting their uncertainties, and hopefully you'll learn something by making that comparison. Sometimes you make the comparison and you still don't know, and sometimes you say, gosh, let's find another technique, measure this with another technique so that we can be sure it wasn't just that the measurement technique was bad. So that can be very helpful. That's another reason why we need that large list of techniques, is because you need to have redundant measurement capabilities to be able to really be confident of something.
All right, we'll go around one more time. Any questions here at headquarters? We have one over here in the corner.
Thank you. Hi, Paul. Vicki Crisp. The flow visualization is very helpful to the researchers to understand what's going on. And you talked about future work is going to look at the quantitative measurements. Are there particular barriers that you have to overcome in order to access that quantitative data? I'm not sure that you address that.
Yeah, the reason why I only showed like 3 big experiments with the cars and Rayleigh scattering, and then with the PLIF I showed, 20 or so different experiments we've done, is because it's just easier to take flow visualization. It's just point and shoot practically. I mean, there's more to it than that, but when you do a quantitative measurement with something like PLIF, you have to check the linearity of your camera and your photodiode you're using to measure laser energy, and you have to have control over the seating of the NO, make sure that stays steady. And there's like this whole extra Pandora's box of issues that you open up when you try to do quantitative measurements. That is, you have to have control of all those things. Whereas it's pretty easy just to get flow visualization. So that's really what it is. It's very time consuming to. And then when you do that, you then want to do a furnace measurement or something, so you can confirm that you've with some accuracy that you have a measured parameter that you can hang your hat on. So yeah, it's a lot harder to do. That's the biggest thing. And actually, we planned to do quantitative work much earlier than this, but we had so much success with just the flow visualization and people encouraging us to do more of that we've really focused on the flow visualization. But I have a new student who's starting up, and he's going to be working on the temperature measurements, and our new hire is going to be working on the velocity measurements, and so we're really excited about that. Yeah.
All right. Any other questions here in the audience? All right. With that, we'll conclude today's presentation. I'd like to thank everyone for joining us today, and in particular, Dr. Paul Danahy for his time from the Langley Research Center. Thank you. And with that, if you'd like more information about any of NASA Aeronautics programs and projects, go to the web at www.aeronautics.nasa.gov. Thank you.